Welcome. In this video we will be talking about IEEE 754 and its consequences, so that by the end of this video you will be able to demonstrate the impact of having just finite precision available. So we already saw that computers store numbers as binary floating point numbers in engineering notation, but they do this in a predefined sequence of bits that we will talk about today. So just as a reminder, binary floating point numbers in engineering notation have the following form. There's a plus or minus, a sign for the number, then there is the hidden bit 1 dot, and then there are bits for the mantissa, and then times 2 to the power p, where p is the exponent. Now, a computer therefore has to store one bit to indicate the sign of the complete number, and the way the definition works is that that sign bit is equal to 0 if the number is positive, or the sign bit is equal to 1 if the entire number is negative. Then the computer has to store the binary digits of the mantissa, and we call these binary digits bits. So there are these bits from the mantissa the computer has to store. And finally, the computer has to store the exponent p. Now, in these numbers here, we typically give p as a decimal number, but of course the computer has to store this as a binary number made up out of individual digits. Now, the question is then, how many bits do we use for the mantissa and the exponent? Well, that is defined in the IEEE 754 standard. So the first number type that is defined in the standard is called half precision. It uses a total of 16 bits. And if you recall that 8 bits form 1 byte, so 16 bits are 2 bytes of storage for half precision numbers. Those numbers have one sign bit to store the sign of the overall numbers. And then the standard defines that 5 bits are used for the exponent, and the remaining 10 bits are used and available for the mantissa. The next number type that is defined is called single precision. It uses 32 bits, or 4 bytes. Again, one sign bit, but now 8 exponent bits, and the remaining 23 bits are used for the mantissa. Next in the definition is double precision, which doubles the number of bits used from 32 to 64 bits as compared to single precision, one sign bit, and now 11 bits reserved for the exponent, and the remaining 52 bits for the mantissa. And then finally, the definition defines quadruple precision, which uses 128 bits to store the numbers, one sign bit, 15 exponent bits, and the remaining 112 bits are reserved for the mantissa. So those are the numbers that are defined in the IEEE 754 standard, but additional newer definitions have come along since then. And I just want to point out one here that is interesting for machine learning, artificial intelligence, and that's the bfloat16 number type that uses the same number of bits as half precision numbers, but distributes the number of bits between the exponent and the mantissa slightly differently as compared to the half precision numbers. So bfloat16 has one sign bit. It has 8 bits reserved for the exponent, so the same number as single precision. And then it only has 7 bits left to define the mantissa. Okay, so let's look at some examples, what the consequences and what the meaning of this IEEE 754 definition is. The first thing that comes across is that there is no bit to define the sign of the exponent. We have a bit to define the sign of the overall number, but the exponent p, there's no sign bit as defined in IEEE 754, but we have to be able to store negative exponents as well. So the solution offered in the definition is to use an offset. And that offset is called a bias, such that half the available exponents are smaller or equal to 0, and the other half are larger than 0. So let's look at these exponent bits. For example, for the half precision definition and the double precision definition. So for half precision numbers, we have 5 bits for the exponent. And for double precision numbers, we have 11 bits available. Now, if we have in general an m-bit binary number, that m-bit binary number can range from all zeros, right, in the bits. So that would be the number 0. To the largest possible we can have is bits of all 1, right? So that largest number would be 2 to the power m minus 1 if we have m bits available. So that means for the half precision, that would be the largest possible value would be 31. And for double precision, the largest possible value would be 2047. Now, we are going to reserve exponents of all 0 bits and all 1 bits for something special down the road. So those bit sequences will not be available to us. So the only available exponent values would be the smallest possible is just a 1. And the largest possible would be all 1s, except the last bit is a 0. So that would be 1 less than 2 to the power m minus 1, so 2 to the power m minus 2. Those are the available bit values for our exponent. Now, half of those are supposed to be smaller equal to 0, and half are supposed to be greater than 0. Okay, so the offset, therefore, this bias has to be half of the available values. And the available values are from 1 to 2 to the power m minus 2. So half of that is 1/2 2 to the power m minus 2. That is 2 to the power m minus 1 minus 1. So that is the offset. Okay, so for a half precision number, the bias would be half of 30, so 15. And for a double precision number, the bias is 1023. So now how do we go from the true exponent to the bit sequence and vice versa? Well, to go from the bit sequence, so the value that is stored by the computer, from there to the exponent, we are going to subtract the bias. And that means that the smallest possible exponent in the bit sequence is 1. The corresponding true exponent would be 1 minus the bias. So that means for half precision number, the smallest possible exponent is -14. And for double precision numbers, the smallest possible exponent is -1022. Similarly, the largest possible exponent is, in terms of bit sequences, 30. Now we subtract the bias. That means that for half precision number, the largest possible exponent is 15 as a decimal number. And for double precision numbers, it's 1023. Now, if we want to go the opposite direction, convert a decimal exponent p, a true exponent p, to the bit sequence, we have to do the inverse operation. So instead of subtracting the bias, we then have to add the bias. Okay, so let's look at half precision and double precision numbers as examples. So a half precision number has 10 mantissa bits, shown here in green, and then we have an exponent that can range from -14 to +15 as a decimal number. And a double precision number has a total of 52 digits, 52 bits for the mantissa, and then an exponent that can range from -1022 to +1023. Okay, so what are the consequences? Well, the first consequence is that we cannot write a true 0 in engineering notation. And that's because we always write numbers in engineering notation having a 1 to the left of the binary point. So we need a special way to store the true number 0. And the special way that the definition IEEE-754 defines is to set all mantissa bits and all exponent bits to 0. And recall before, when we discussed the bias, I said we cannot use exponent bits all zeros, right? That is reserved. Well, it's precisely reserved to store the true value of 0. Okay, so if I have all bits equal to 0 and the exponent bits all 0, so one below the smallest possible minimum exponent, so negative 15, that would be defined as 0. And similar, all mantissa bits equal to 0 and times 2 to the power negative 1023. So one less, one below the allowable range, that is defined as meaning 0. Next curious thing is that we still have a sign bit available, which means that depending on the sign bit, we can actually indicate either plus 0 or minus 0. Okay, that's the consequence of having the sign bit available. Next, there is a smallest non-zero number. So we're looking for numbers that are as close as possible to 0. That means, what do we do with the mantissa bits if we want to make the number as small, close to 0 as possible? We would set all the mantissa bits to 0, right? So there are all zeros here in the mantissa bits. And what do we do with the exponent? Well, we make it as small as possible, right? So that would mean for the half precision numbers, we have 1.0 times 2 to the power negative 14. It's about 6.103 times 10 to the negative 5. And for double precision numbers, the smallest possible legal exponent is negative 1022, all mantissa bits 0. And that number is 2.22 times 10 to the negative 308. And in MATLAB, you can actually get this number if you type in real min. That will give you the smallest possible double precision number, because by default, all arithmetics in MATLAB are in double precision. Okay, next up, the result of a computation smaller than this smallest non-zero number is an underflow, because we cannot represent this number anymore using our definition. Now, underflows are either set to true 0, stored as a so-called unnormalized number, or the program causes an exception, meaning it crashes. Okay, next. We need a special way to store plus or minus infinity. And that is done in the definition by setting all mantissa bits to 0 and all exponent bits to 1. And recall that before, when we talked about the bias, we reserved all exponent bits equal to 1. So this is why we reserved them, in order to be able to store infinity. So all mantissa bits equal to 0 and all exponent bits equal to 1. That is the number infinity for half precision, and similarly for double precision. That is defined as meaning infinity. And together with the sign bit, we can then have plus or minus infinity. Next, we can identify invalid floating point numbers, and those are indicated or named NaN, which stands for not a number. Examples of invalid floating point numbers are square roots of negative numbers, as an example. And the special way to store a not a number is to set all exponent bits equal to 1, so similar to plus or minus infinity, but not all mantissa bits to 0, right? So all mantissa bits equal to 0 would indicate plus or minus infinity, which in some sense is not a number as well. But having them not equal to 0 indicates an invalid floating point number, a not a number. Okay, so this would be not a number for half precision, and this would be not a number for double precision. And the mantissa bits can be any combination of values except all 0. Okay, next, there's a largest non-infinity number. Similar to having a smallest non-zero number, there's a largest non-infinity number as well. So we're after making our numbers as large as possible. So what would we have to do with the mantissa to make the number as large as possible? Well, we would set all the mantissa bits equal to 1. Okay? And then what would we do with the exponent? Well, we would make the exponent as large as possible, which would be for a half precision number 2 to the power 15. And for a double precision number, the largest exponent is 1023. So if we calculate those numbers, the largest possible non-infinite half precision number is 65,504. And the largest double precision number is 1.7976 and so on times 10 to the power 308. And you can get this largest possible double precision number in MATLAB if you just type in real max. I compare that to real min, the smallest possible non-zero number. Real max is the largest possible non-infinite number. Next consequence is that the result of a computation larger than this largest non-infinite number is an overflow, similar to the underflow before. Now, overflows are either set to infinity, plus or minus, or stored as an unnormalized number. Now, in most cases, depending on the programming language, the program can also be caused to throw an exception, meaning we can make it crash. Okay, next consequence. There are only a finite number of numbers that can be stored exactly. Now, irrational numbers can't be stored exactly, right? That kind of makes sense because we only have a finite number of bits, digits, meaning available. But there are some curious numbers that we would think initially don't cause any issues. An example is the decimal number 0.1. Well, it turns out if you try to convert 0.1 as a binary number, you will need infinitely many digits, right? The remainder will never be 0, which means that we cannot store this benign-looking number in decimal 0.1 as a binary number exactly. We will make an error when we try to store this number exactly. And in fact, there is an error associated with storing most numbers because they cannot be expressed exactly with the number of mantissa bits that we have available. Okay. Next, there are intervals between numbers. Now, the smallest interval depends on the number of mantissa bits that we have available and the exponent p. So here's a half precision example. If I have a number like this, half precision, I have 10 mantissa bits times 2 to the power p, where the exponent is just p. What is the next larger number, right, if I have this number? Well, I can generate the next larger number by just increasing the last bit of the mantissa by 1. So in this example here, that last bit of the mantissa is 0. So the next larger number would be just increasing this 0 to the number 1. That is the next larger number. So what is the difference between those numbers, right? It is equal to everything 0 except the last mantissa bit being 1, right? That's the smallest difference. So if we convert this, this would be equal to 2 to the power p minus m, because now I have to move this binary dot m positions, the number of mantissa bits, over to turn this into a binary floating point number in engineering notation. So the result is 2 to the power p minus m. That is the smallest difference in numbers. So what is this for half precision numbers? Right, the smallest difference is all zeros, 1, 1 at the end. If the exponent p is equal to 0, so order 1 numbers, the smallest difference is 9.76 and so on times 10 to the power negative 4. And for half precision numbers, right, we have more mantissa bits times 1 at the very end times 2 to the power 0. If we're looking at order 1 numbers, that smallest difference is 2.22 times 10 to the power negative 16. And in MATLAB, you can get this number, the smallest difference between order 1 numbers, by typing in the command EPS. Okay, so let's do one example here to see what the impact of this smallest possible difference is. The question is, can a computer tell the decimal numbers 65.01 and 65.04 apart if half-precision numbers are used. So are these two numbers different for a computer if we use half-precision? Well, the smallest interval, as we just derived, is depending on the exponent in binary notation of these numbers. And that exponent p is rounded down of the logarithm of the number divided by the logarithm of 2. So let's take 65.01 as an example. So we have as the exponent p the floor of the logarithm of 65.01 divided by the logarithm of 2. That is rounded down 6.022. So the exponent is equal to 6. So the smallest interval we can tell apart in half precision is p is equal to 6. So 2 to the power 6 minus the number of mantissa bits for half precision, which is 10. So the smallest difference is 2 to the power 6 minus 10, which is 2 to the power negative 4, which is 0.0625. That is the smallest possible number, or the smallest difference between numbers that a computer can tell apart. Now, we have the number 65.01 and the number 65.04, and the difference between those two numbers is 0.03, right? So the smallest difference that a computer can tell apart is 0.0625. So it is larger than the difference between these two decimal numbers, which means that the computer will not be able to tell these two numbers apart. To the computer, these two numbers are identical. So this slide now summarizes all the consequences that we went over that arise from using a certain number of bits for the mantissa and the exponent that are defined in IEEE 754. Now, 754 defines these different precisions from half precision all the way to quadruple precision. So which precision should one use? Well, that depends on two things. One, on cost. Because the more bits you will use, the more needs to be stored, and the more bits the computer needs to compute with. So it becomes more expensive to use more bits to store your number. But on the flip side, right, we have to talk about accuracy, right? The more bits we have, the larger the possible numbers that we can store, the smaller the difference between adjacent numbers becomes. So it's an accuracy question. So we will have to deal with a trade-off of cost, pushing us to use less bits, versus accuracy, where we would like to use more bits depending on what error is tolerable. But that will be the topic of the next video. Thank you for watching.